Hello, in this video I'll be going over the introduction to instantaneous rate of change, otherwise known as the derivative. So, in this video I hope you're familiar with average rate of change. So, I'll just go over that real quickly. So, an average rate of change is, consider a function, let's just say it's just some function f of x, right? The average rate of change is the gradient between 2 points of a line, pretty much. So you have a curve here, and you're just finding the gradient between 2 points on that line. Okay, so it's like the average steepness between 2 points. Now in calculus, we want to find, let's say I'll draw a bigger axis. Let's say we have a curve like this, and let's say you wanted to find the steepness at that particular point, like the instantaneous steepness. No average point, so there's no 2 points here. We don't make a line through 2 points. You want the instantaneous, the gradient of any curve f of x at any point. How would we find that? Well, let's just take a look at just a normal curve. Let's say we have just a parabola here. Let's have y equals x squared, which is just equal to f of x. Actually, no, we don't, even a more generic example. Let's just say we have y equals f of x here, right? And you wanted to find the instantaneous, you want to find the gradient of a tangent line at any point on this curve, right? So recall that gradient is the change in y over the change in x. And we can calculate that gradient with this formula that we've established before. So y2 minus y1 over x2 minus x1. So that's basically saying if you have x1, y1, and you have x2, y2, you can find the gradient if you had 2 points. So let's just keep this idea in mind. So gradient is 2 points like this. Let's keep this idea in mind. I'm just going to make it smaller so it's out of the way. Just make that a bit smaller. Alright, and let's consider our function here. And let's consider we have a point x, f of x, right? So that's our first point. So x is here. Therefore, our f of x value is going to be here. And let's say we had some distance h and between our next 2 points, right? So I'm just going to change how this curve looks a bit, so it's a bit bigger. Let's say we had a distance h between our 2 x points. So this point would be x plus h. Therefore, this would be, instead of f of x, it would be, whoops. Sorry, my pen's not working. I'm just going to move this because my computer's playing up at the moment. I'm just going to move this down here so we have more drawing room. Alright, so we have a point x, and the distance between its next point is just a distance h. So this point here would be x plus h. X is any point on this line here. This is the x-axis, and this is the y-axis. So this would be f of x plus h, right? So our 2 points are x and f of x, and our other points is x plus h and f of x plus h, right? So this is x1, y1, x2, y2, right? We know that gradient is this, so why don't we just plug in these 2 points into that formula? So let's go, so y2 would be f of x plus h minus y1, which is f of x, divided by x of 2, which is x plus h, minus x of 1, which is x. So our gradient, simplifying that, is f of x plus h minus f of x. Up here is f of x plus h and the bottom here is h. So that's the gradient of this arbitrary diagram we have here. Now, to find the instant rate of change, this distance h in here, I want you to imagine this point getting closer and closer to this point. So they're getting closer and closer together. So we need this distance h to approach 0. So I'm just going to rub this out here so we have more room for our stuff. Right. So this is our expression for our gradient. Now I want to introduce an idea of a limit. So we're going to put a limit. So we're going to have the limit as h approaches 0. And this should give us, basically, if this distance comes 0, these points are going to be on top of one another. Oh, sorry. Which would give us an instantaneous gradient. Okay? So you might be familiar with this. This is the first principles of the derivative. So this is where the first principles comes from. So we want our h to be 0. So these 2 points are on top of each other. So it's an instantaneous gradient. Okay? So, why do we have an e there? I'm going to get rid of that real quick. Sorry. Alright, so if you want to copy that diagram down, I'm just going to rub it out now. So this is where we got our first principles from. So, going on to that idea, I want to find a tangent line to any function at any x point, just using what we've established up here. Okay? So let's say we have an x-axis and a y-axis, and we have f of x equals x squared. So we have this function here. And I wanted to find the gradient when x equaled 1, like the instantaneous gradient at that point. So what I would do here is I go f of x equals x squared, therefore f of x plus h is equal to x plus h all squared. Okay? So expanding this is going to be x plus h times by itself, and then you will do FOIL, first, outer, inner, last, so you get x squared plus xh plus xh plus h all squared, so x squared plus 2xh plus h squared. Okay? Now I'm going to rub all this out so we have simplified it a bit more. So I'm going to move this up here. That is corresponding with our x-axis. I'm just going to rub out our x-axis for a second and move it down here. Right, and then draw that back in. There we go. Make that a bit shorter actually. Right, so the limit as h approaches 0 of f of x plus h, which is x squared plus 2xh plus h squared, minus f of x, which is x squared, all over h. We can see those are going to cancel, so we're left with the limit, limit as h approaches 0 of 2xh plus h squared over h. Right, so the top half of our fraction, we can take our factor of h. So the limit, and yes, you have to write limit every time when you're doing first principles, limit as h approaches 0 is h over 2x plus h all over h. That will cancel, so you're left just with the limit as h approaches 0 of 2x plus h. Since h approaches 0, the instantaneous gradient is 2x, or the first derivative, so is 2x. Okay? So if we want to find the if we want to find the gradient at that point, we would just plug in x equals 1. So therefore our gradient, our instantaneous gradient at x equals 1 on the function f of x equals x squared is just 2. Because we put that into there, so we cut 2 times 1 equals 2. Okay? So that's the first principles of basically the derivative. Because what we found right here is a thing called dy dx, or you might see it as f dash of x. So we just found this is a thing called the gradient function. So I'm just going to write some stuff up here. So I'm going to get rid of all this first principle stuff, and I'm going to try and articulate what this is pretty much. So we've shown where we've shown where this first principles comes from. It gives the instantaneous gradient of any function. But what does this this gradient function actually mean? So when you apply this law, it gives you f dash of x, or you may see it as dy dx. Okay? So just in terms, so y equals x squared, and we discovered that dy dx is equal to 2x. What does this function actually mean? What does this tell us? So let's just draw the line, not the line, the function y equals x squared. Okay? So y equals x squared. When you plug in an x value into here, you get a y coordinate. When you plug an x value into this thing, it gives you a dy dx. It gives you a gradient at that point. It gives you a steepness. That's what it gives you. Okay? So at the point, let's say on the function x equals 1, we want to find the point and the steepness at that point. Steepness. I can't spell that. That is definitely wrong, but you know what I mean. So we have our normal function y equals x squared, and we have our derivative dy dx equals 2x. Plug that in. That gives us a coordinate. So that gives us a position. Plug this into here. It gives us the gradient, the steepness at that point on the function. That's pretty much what it gives us. And you'd notice as the x values increase with this particular function, it gets steeper and steeper, because with a parabola, it gets so steep it can become undefined, pretty much. So just imagine you're having dropping a ball into this parabola and it rocking back and forth. It'd be like, the steeper it is, the faster down the ball is going to go, but the flatter it is, the more likely it is to stay. It's curvature. Okay. And so instead of doing the first principles, they basically discovered for any polynomial, if you have let me just rub this out. So yeah, this here works every time, but it is way too long. So they discovered that if you have a polynomial, let's say you have y equals ax to the n, where a is a constant and n is some integer. So it could be like 2, 3, 4, yada yada yada. If you want to find dy dx, you basically bring this power down the front, n times a, and you reduce the power by 1, so x to the n minus 1. Okay, so if we go y equals x squared, dy dx, we bring this down the front, so we have a 2, and you subtract this power by 1, so x to the 1, which is just 2x, which we found before with first principles. So this is the rule for differentiation with a polynomial. Anyway, I think that's enough for this video. This was just a basic introduction to gradient. I'd say it was a medium level video. If you didn't have any intuition coming into this video, I would say this was a bad video to watch. There are much other better videos, but if you are kind of familiar with derivatives and calculus, I think this is an okay video, but I'll probably make a better video explaining this. So this is basically explaining where the steepness comes from, and I've just gone into another topic, or further into the same topic, but I'll leave this for another video. So thank you so much for watching. I hope you learned something.